Greetings, students. So today we're going to talk about exponential functions. Okay, so the exponential functions have generally this form right here, ab to the power x minus h plus k, where h would be your horizontal shift and k would be your vertical shift. And you can have exponential functions could be exponential growth or exponential decay. And that really depends on the base of your exponent. So if you have on the base of your exponent, so if you have the base that is greater than 1, strictly greater than 1, then you have exponential growth. For example, y equals 2 to the power x. So if that's the case, then your exponential function will look like this. So it will be growing. However, if you have the base that is between 0 and 1, then you will have an exponential decay. So for example, if you have y equals 1/2 to the power x, then you will have an exponential decay function that will look something like this. Okay, so these are your two general shapes depending on whether you have growth or decay. Now, let's look at our first examples and we'll see how to graph these functions accurately. And then we'll discuss domain, range, horizontal asymptote, y-intercept. All right, so we have the function f of x equals 3 to the power x. So what we're going to do is we're going to make a table of values. And we can substitute numbers from -1, 0, 1, and 2. Okay, so we'll have 3 to the power -1, which is 1 over 3. Then 3 to the power 0, which is just 1. 3 to the power 1, which is 3. And 3 to the power 2, which is 9. Okay, so this is our table of values. And let's plot this point. So we have -1 and 1/3. So it's a little bit over here. 0, 1, 1 and 3, 2 and 9. So 9 is going to be somewhere here. So if we now keep in mind that if we continue plotting smaller and smaller values of x, then our function will be approaching 0. So let's look at the calculator here. We don't need that. So let's say we have 3 to the power, let's say -2. Then we have 0.111 repeating, then 3 to the power -3. Then 3 to the power -4. And no matter how small, how big our negative number is, so let's say we have 3 to the power -10. Notice that this is scientific notation, so it's 1.69 times 10 to the -5th power. So our values get smaller and smaller, but they will never equal to 0. So we are approaching 0. So therefore, our graph of the function will look like this. And then we are approaching our x-axis, but we will never cross the x-axis. So this is our f of x function. So therefore, it looks like since we're approaching this x-axis, that it seems like we have an asymptote here. We have an asymptote at the x-axis. So now, let's think what our domain is going to be. So we're thinking, what kind of numbers can we substitute in for x? Do we have any restrictions? Well, if we look at this, we already saw that we can substitute negative numbers, we can substitute 0, and we can substitute positive numbers. So it seems like there is no restriction on our values. Therefore, the domain of exponential function is from -infinity to infinity. Now, remember, domain deals with the x values. The range, however, that deals with y, well, it seems like there is a restriction because we are approaching 0, but we're never actually reaching 0. So, but then we are above the x-axis all the time, and we're never approaching that 0 value. Therefore, our range is going to be from 0 to positive infinity. And notice that the 0 has a parenthesis because we will never be able to include that 0. We already saw that we have a horizontal asymptote, and well, the equation of this horizontal line is y equals 0. So that is our horizontal asymptote. Remember, has to be written as an equation, not just 0. Has to be y equals 0. Finally, y-intercept. Well, we're finding the y-intercept the same way we found it in the past. We're substituting 0 for x to find y. So therefore, we have y equals 3 to the power 0, which is just 1. We already had that in our table. So the y-intercept will be 0, 1. Has to be written as an ordered pair, as x and y coordinate. Now, let's see what happens if we apply some transformation. So here, in part B, we have f of x equals 3 to the power x minus 2. Minus 2. So that means that we're bringing everything down 2 units. So therefore, we can make a new chart. We can make x and y chart. So we still can use the same x values, -1, 0, 1, and 2, but then all of our y values will be, we're subtracting 2 from them. So for example, when we have x equals 1, I'll write this one out. So we have 3 to the power 1, but then minus 2. So therefore we'll have 1/3 minus 2, which is -1 and 2/3. And then we're basically gonna do the same thing to everything else. So we're gonna take our value of 1, but then we're subtracting 2 from that value. So our next one, so 1 minus 2 is gonna be -1. And then we're gonna take our value of 3, we're subtracting 2 again. So it becomes 2. And then we're gonna take 9 and subtract 2 from it, so it becomes 7. So these are our new values. So now notice we will be crossing our x-axis. So our new points will be -1 and -1 and 2/3, so it's somewhere here. Then 0, -1, 1, 2, and then 2, 7. Something is a little off. 0, -1 is right. -1, -1 and 2/3. Maybe it is correct. Okay, so now our graph, so 2, 5, 6, 7. Okay, so our graph will look like this. Now let's see what happens to our asymptote. Well, our asymptote is also moved down 2 units. So that means that our asymptote is going to be at -2. And I think the reason why, yeah, so the asymptote has been moved down 2 units. Therefore, this is our graph. So this is our function 3 to the power x minus 2. Well, this one was just 3 to the power x. Okay, so let's talk about our domain. Well, our domain is still all real numbers because we can still substitute all kinds of numbers in for x, negative and positive. So it's from -infinity to infinity. The range, however, now, notice that our function has been brought down 2 units, but we still have that asymptote at -2. Therefore, the range would be from -2 to infinity. Horizontal asymptote, in a similar way, we brought down our asymptote 2 units, so it's going to be y equals -2. And now the y-intercept, we can kind of see it on our graph. That's when x is equal to 0 right here. You can, once again, if you don't have this table already, you can calculate what it is. It's going to be 3 to the power 0 minus 2 Please remember that anything to the power 0 is 1, so 1 minus 2 is equal to -1. But you do need to remember to write this as an ordered pair. So please notice your domain and range. These parentheses imply in interval notation. So it basically says that y is strictly greater than -2, and x is just all real numbers. So just like in all of the other lessons that we had, please remember, you can either be asked to use an interval notation or inequality notation. You need to know both, but that's what this notation means. And notice that your asymptote is never included. Also notice that the value of the horizontal asymptote, this number and this number, are always going to be the same. Okay, so this is how you graph an exponential function. So now let's look at an exponential function with a bit more transformations. So question is, how has the graph been shifted from the parent function? Then we're gonna graph it and then find domain, range, and all of those other things. Well, let's look at our graph. So we have -1 in the power. Sorry about that. -1 in the power. So remember that anything that's inside of the function, that's our shift left and right, and it follows the opposite sign. So if it's x -1, we're shifting everything to the right, and then we have +3 on the outside. Well, that means that we're going to be shifting everything up. So therefore, we're going to shift right 1 and then up 3. Okay, now to graph this, we are going to make a t-chart again. And we can substitute numbers such as -1, 0, 1, and 2. And now we're going to find our y values. So I'll show a little bit of work here. So y equals 2 to the power, actually, let's see, have some room. So y equals 2 to the power -1 minus 1 plus 3. So that gives us 2 to the power -2 plus 3. Then remember that the negative power makes your 2 into a fraction. So it becomes 1 over 2 to the power 2 plus 3. And then 1 over 2 squared is 1/4. So therefore we'll have 1/4 plus 3, and therefore you get 3 and 1/4. Okay, then you have the same thing for 0. So you have 2 to the power 0 minus 1 plus 3. You can use a calculator to do this, and to speed this up, it will give us 3 and 1/2. Then 2 to the power +1 minus 1 plus 3. That is, of course, 0. 2 to the power 0 is 1. 1 plus 3 is 4. And then 2 to the power 2 minus 1 plus 3. So this gives us 1. So 2 to the power 1 is 2 plus 3 is 5. So these are our points. So -1 and 3 1/4. 0 and 3 1/2. 3 1/4 would be a little bit lower. So 0, 3 1/4. 0 and 3 1/2, then 1 and 4, and 2 and 5. Okay, so we have these points. Now, it looks like we are approaching 3 right here. So that is our asymptote. Therefore, we're going to get the graph like this. So this is our f of x equals 2 to the power x minus 1 plus 3. Now, some of you will say, well, how do I know that 3 is the asymptote? Well, that's actually not that difficult because notice we said that we are shifting everything up 3. So our original asymptote would have been, if there was no shift, it would have been at the x-axis. This would have been the original asymptote. But since we're moving everything up 3, this asymptote would be shifted up 3. 1, 2, 3. So that's where our asymptote is located. So therefore, we know that the asymptote would be at 3. In other words, this number right here will always give us the horizontal asymptote. Okay, so therefore, our domain, the exponential functions, really, it's the easiest question. They always have the domain of negative infinity to infinity. You can always substitute any number for x, negative, positive, zeros. But the range, the horizontal asymptote, we're going to talk about the range here in a second, is always going to be y equals whatever the vertical shift is. So if it's plus 3, that means that it's going to be y equals positive 3. Now the range, you do need to look at the graph and see whether the graph is above or below the horizontal asymptote, because sometimes the graph could be flipped around the horizontal asymptote. So in this case, the graph is above the horizontal asymptote, therefore the range would be from 3 to infinity. Now the y-intercept, once again, we already have the y-intercept because we used it in the table. It's going to be 0 and 3.5. But if you did not have that value, just as always, you substitute 0 for y, and you get 0 minus 1 plus 3. And once again, that will give you 3.5. And please remember to write this as an ordered pair. Okay, so this is our exponential function shifted. Okay, now exponential functions have a lot of applications, and one of the most commonly known application is we can find compound interest used in exponential functions. And we have two types of compound interest. We have compound interest that's compounded n times a year, and then we have continuously compound interest. So compound interest that's compounded n times a year means that, let's say, you have a yearly compound interest. That means that you put some money into your account, let's say $100 at, let's say, 2% interest. So a year passes. During that entire year, nothing happens to your $100, but at the end of the year, your value adds 2%. So at the end of the year, you will start the next year with $102. Then you have $102 for the entire year. Nothing happens. And then at the end of the year, you add 2% of 102, and then you get the next value. So that's what we mean by compounded n times per year. So when that happens, we use the formula right here. So this is interest compounded n times per year. In this case, we probably should identify our parameters. So P stands for principal, which is your initial amount. So this is what you start out with. Then R is your rate of compound, and has to be written as a decimal. Then N is the number of compounds per year. And T is, of course, time. And usually our time is in years, but that could change. Okay, so now our N will change depending on how many times per year we compound. So for example, if we compounding our interest yearly, then N is equal to 1 because it's done once a year. Quarterly, that means it's done 4 times a year, so N is equal to 4. Monthly, well, monthly means that it's compounded 4 times a year, so N is equal to, 12 times a year, every month, which is 12 times a year. Daily is N equals 365. Now, if it's compounded continuously, then technically your N becomes infinity because it's compounded every not even millisecond, even more often than that. So if it's compounded continuously, then you just change the entire formula. The formula becomes this right here. Now, where your E is a special number, it's called Euler's constant, and it's approximately equal Sometimes forget what it is. It's about 2.718 and so on. So 2.178 and so on. But there is a special button on the calculator that we're going to be using. Okay, so if it's compounded continuously, that's the only time when we're going to be using this formula. So it's A equals P e to the power RT. We sometimes call it the PERT formula. It's an unofficial name. It's not actually called that, but we call it PERT because that's what it spells. So technically, the way we've got it is by n going to infinity, and it just happens so that when n goes to infinity, then the argument approaches 2.178. Okay, so let's look at our first example. So suppose you're buying a house for, I don't know, houses in Bloomington are pretty expensive right now. So let's say $300,000. And you're taking a mortgage at, let's say, 6% interest rate. How much money will you end up paying for the house? Well, that's kind of, this question is actually not very accurate because that's how much money you're going to end up paying for the house if you make no payments at all. So basically, if you don't make any payments within 15 years, none at all, and you just sit there for with 6% interest rate, how much how much your debt will accumulate. So let's say how much will you end up paying for the house? Once again, we're gonna make like if you make no payments. Because if you start making payments, that's a much more complicated question. It's actually a question of differential equations. That's something is studied in college. So if we make so if our interest accumulates yearly, sorry about this again. That means that n is equal to 1. So if we're doing it for 15 years, then it's going to be 300,000 times 1 plus. Now our R would be 6% interest, but we have to convert it to a decimal. So it's going to be 0.06. We already know n is 1, and then our t will equal to 15. So it's going to be 1 plus 0.06 over 1 to the power 1 times 15. Okay, so you just type this whole thing in a calculator and let's see what we are going to get. I'll just pause this video so you don't have to wait. Okay, so if you make no payments for 15 years on your house, you will have to then pay $718,167.46. Once again, that means that you're making no payments whatsoever. So your house value, well, I wouldn't say value, but what you owe to the bank will way more than double. Now, if we do it for 30 years, clearly you will substitute 30 instead of 15 and you'll find that value. So we're not going to do 30 years. Let's just talk about quarterly and then continuously. What happens then? Okay, so for continuously, same idea. For quarterly, it's the same idea, except now n is going to be equal to 4, but our r is still going to be 0.06, and our t is still going to be, let's say, 15. Okay, so we'll have 300,000 times 1 plus 0.06, but now divided by 4, and then now it's 4 times 15. And we're gonna calculate that value. Okay, so now that value would be $732 $1,965.93. Once again, that's assuming that you're making no payments whatsoever. Then how much you owe to the bank will accumulate. Of course, by this time, the bank will repossess your house. This is very theoretical. Now, finally, continuously. Now, for continuously, there will be no n. Notice there is no n here at all because continuous formula is PERT. So there is no n. Instead, we have this constant e. So let's see how we can do this. So first of all, let's write this out. So it's going to be 300,000 times e to the power 0.06 times 15. Okay, so on a calculator, so I'm going to use this graphing calculator, but it's all going to be pretty much the same. We'll have 300,000. Now to press E, you usually will press the second button, and then where it says ln, press ln, and it's usually will say E, and usually it will set up the power already. And then you type in the 0.06 times 15. And then we get our amount, which is 737,893. And we're clearly rounding to 2 decimal places since we're talking about money, so it's going to be cents. All right, finally, the last thing we're going to do is talk about solving exponential equations. So for exponential equations, we're going to use something called one-to-one property. And the one-to-one property basically tells us that if we have some base to the power x that is equal to the same base but to the power y, the only way for that to be true if your powers are the same. That means that x is equal to y. Now, that is nice if you have like 3 to the power x plus 2 equals 3 to the power 5. Then all we do is just set up the powers equal to each other because the bases are the same. So the only way for that to be true is if x plus 2 is equal 5, and therefore you find your answer, which just happens to be x equals 3. However, as you can see in our first example, that is not the case. We have the base of 5, and then we have a base of 125. So what we need to do is to rewrite one of these bases in terms of the other. And we're usually going to go rewrite the bigger base in terms of the smaller one. So we can rewrite 125 as 5 to the power 3. So this 125 will be 5 to the power 3 to the power x. Now on the left side, we're still going to have 5 to the power x plus 2. Now, by the properties of powers, 3 and x can be multiplied. Therefore, we have 5 to the power x plus 2 equals 5 to the power 3x. And now we can use one-to-one property. Since the bases are the same, that means that our powers have to be also the same. So x plus 2 will equal to 3x. And now from here, we have to solve this. Well, it's a linear equation now. So we're going to subtract our x's. Therefore, we have 2 is equal to 2x, and then divide by 2, and therefore we get 1 is equal to x. Okay, and we can mentally check it, because if we substitute 1 in for x here, we'll get 5 to the power 3. We substitute 1 in here, it would be 125 to the power 1, but we already know that 5 to the power 3 is the same thing as 125. So that does work. Now let's look at the next example. This one is a bit more complicated because we have 1/4 to the power 2x equals 16 to the power x plus 5. So we have to think how to make these bases the same. Well, there are several different ways that can be done. So it doesn't have to be done in this one particular way. However, we can see that 16 is the same thing as 4 squared. Okay? At the same time, 1/4 is the same as 4 to the power negative 1. So in this case, we can change both of our bases to become we can change both of our bases. We can change 1/4 as 4 to the power negative 1. And then it's to the power 2x. And then we can change our 16 as 4 squared. And then we have x plus 5 on the outside. Now from here, we can multiply these powers. So therefore, it's going to be 4 to the power negative 2x and 4 to the power 2 times x plus 5. So now notice our bases are the same. Therefore, we can set the powers equal to each other. We're once again going to use the one-to-one property. Therefore, we'll end up with negative 2x equals 2 times x plus 5. And now we're just solving this linear equation. Negative 2x equals 2x plus 10. In this case, maybe move 2x to the other side by subtracting 2x on both sides. So we'll end up with negative 4x is equal to 10. And therefore, x is equal to 10 or divided by negative 4 or negative 2.5. And that would be our value here. So when you solve exponential equations, you have to make the bases the same. You have to think about which numbers, how can we rewrite those. Sometimes you just make one of the bases the same, but sometimes you make both of them. You change only one of the base. Sometimes you change both bases. And once again, usually change the bigger number to become smaller. So rewrite, we're going to write it, rewrite a bigger base as a smaller number. What I mean by that is we looked at 125, we rewrote it as 5 to the power 3. We looked at 16, we wrote 16 as 4. So we're making the bigger number into smaller. But, with 1/4, it went the other way around, but we just made our power negative. Okay, so this is our lesson. Hopefully, it is clear. If you have any questions, please let me know and I will be happy to answer them. Have a good day. Goodbye.